Hey guys, it's Miss Butler. Got a video for you as an introduction to equilibrium. I apologize if it sounds like I'm crying a little during this video. I'm making the video on the very last day of summer. So it's probably October for you, or if you're in honors, maybe like May. Summer's right around the corner. But for me today, summer is about to end and I'm pretty upset about it. So again, sorry if it sounds like I'm crying. Just gonna fight through it. All right, so everything we've seen so far in chemistry, the reactions we've looked at have a one-way arrow because we say the reactions go to completion. So basically, we have reactants, they're all used up to make the products, we run out. So like when we did our BCA table, so like we had A plus B makes C plus D. When we did our BCA table, right? One, A or B, or sometimes in cases where it was a perfect situation, one of them ran out, right? We had a superstar, we had a limiting reactant, right? So these completion reactants, we have a limiting, one or more of the reactants totally run out, we make the products, and it's a one-way arrow. The reality is most reactions in the world do not go to completion. So we were looking at a very, very narrow margin of reactions, or we would just, for regular chem, we would just assume they would go to completions to make our lives easier. But the reality is most reactions do not go to completion. So basically, we're not using up 100% of this. There's going to be some remaining. So there's not necessarily going to always be a 0 on the left side of your BCA tables. So what's really going on here is we reach this dynamic state, this back and forth state where some of the reactant turns to product, some of the product turns back to reactant, and we get this back and forth. It's a constant thing. When we have an equilibrium, we're going to use this two-way arrow to signify that it is at equilibrium. That we get this back and forth, the reaction can go in the forward and it can also go in the reverse direction. All right, so let's say we have a reaction and it's at equilibrium. So the reaction has started like it normally would, but then we reach this state of equilibrium. What's really going on is we still have the forward reaction making the products. We still have the reverse reaction where the products are turning back into reactants, but the rate of the forward reaction is equal to the rate of the reverse. Remember, when we're talking about rates, we're talking about kinetics. So this relates to our last unit on kinetics, the speed or the rate of reactions. If you're sitting there and you're looking at a reaction at equilibrium, you might not notice. It probably looks like it's doing nothing. The reason is because the concentration of all the species, reactants, and products will be constant. Okay, I don't mean that the reactants equals the products. What I mean is if I have some reactants, the concentration of A is probably not going to be changing. Why is it not changing? Well, because this forward reaction is happening and it gets used up. But the reverse reaction is also happening and A is getting created. So sitting there looking at it or measuring, you're not going to notice a difference because this is a constant dynamic back and forth. And one thing to note, equilibrium has to happen in a closed system. If I have a flask and we have a reaction happening and it's making a gas, if that gas can escape, right, it's not going to react to go back into the reactant. So it has to be a closed system, got to have a lid on there so we can get this back and forth to be happening. Okay, this slide might look a little overwhelming at first, so I want you to just bear with me. We're going to go through it slow. I have a reaction here. Reactant 1 plus reactant 2 makes product 1 and product 2. Okay, it's a double arrow, which means we have equilibrium. And I want to show you the relationship between kinetics, our last unit, and equilibrium, this unit. So let's just look at the forward reaction. Pretend that this was last unit and we just have a one-way arrow happening. If we wanted to write our rate expression, right, a forward reaction, we would say the rate of the forward reaction, that's this F, rate is equal to little k, the rate constant, times the reactant times the other reactant. Right? That's exactly how we write our kinetics rate law. Well, let's pretend for a second that we're looking at the reverse reaction. Well, now the rate of the reverse reaction is going to be equal to the rate constant, little k, times the concentration of the product and this product. And I'm calling them products just to keep it in context, but really we know when we look at a reaction, we're just taking into account the reactants. So remember, when we go reverse, these are now my reactants making the products. Okay, so I have the rate of the forward reaction, the rate of the reverse reaction. The definition of equilibrium is that when the forward rate is equal to the reverse rate, equilibrium exists. So if I know the rate of the forward is this expression, and I know the rate of the reverse is this expression, I can set them equal to each other. Okay, what if I rearrange and get the k's on the same side? So what if I take both sides and I divide this side by kr and this side by kr? That'll give me this, because those will cancel. And then what if I go a second time and divide both sides by the concentration R1, concentration R2? Divide what you do to one side, you have to do to the other. So those cancel, and we're left with this expression. So instead of saying kf divided by kr, I'm going to give it a new k, a capital K. So these rate constants, kf divided by kr, is going to give me my big K. So big K is going to be equal to the concentration of the products divided by the concentration of the reactants. Where does that come from? It comes from the idea that the forward rate and the reverse rate are equal. So you will see this big K equal something similar to this guy in yellow a lot. And this is the one slide that kind of puts it all together of where it comes from. Okay? 9 times out of 10, I'm going to be honest, AP Chem students forget the relationship that the forward rate is equal to the reverse rate, because you start to see this equation, K equals products divided by reactants, so often. But I do think it's important to show you where it comes from and how it connects to the idea that the forward rate and the reverse rate are equal. A lot of times we're going to look at equilibrium from concentration graphs. So here's what's happening in this graph. We always got to kind of pay attention to our axes. So I have time. So as time is going on, we are measuring the concentration, moles per liter, so this is molarity, of A, B, and C. Okay, right away, here's what I notice. A starts at 0.4 and it ends at 0.15, and I wrote that in for us. I know it's kind of eyeballed. We're just going to go with those numbers I wrote in black. Okay, so A is being used up. So that means A is a reactant because it's being used up. And the other two, B and C, are starting 0.2 to 0.32, so B is being produced, so that's a product. And C goes from 0 to 0.12, so that is a reactant. Oops, I want to switch my colors. Okay, the other thing I notice about this is that A is actually going like twice, it's dropping twice as much as B and C. Like B went from 0.2 to 0.32, it gained 0.12. This guy, C, gained 0.12. A is dropping about twice as fast. So I'm going to put a 2 in front of A because it's dropping twice as quickly as B and C are being produced. Okay, so there's a little equation. But let me show you what else this graph kind of indicates to us. I noticed that there's a certain point in time that the graph becomes leveled off. So if you look right at like 500 seconds, maybe a little after, we'll just say 500, I notice that the concentration of A, B, and C stay constant. Notice they're not equal to each other, but they don't change anymore very much. So this whole region, this whole area past 500 seconds represents what this unit is all about, and that's equilibrium, right? When the forward rate and the reverse rate is equal. So what you see here is that the reaction happens. If I were observing this reaction, I would probably see some of the signs of a chemical change between 0 and 500 seconds. After 500 seconds, the reaction is still happening, but it's at equilibrium. So it's going back and forth. I don't notice that the concentration changes of A or changes of B or C, but it's going the reverse and the forward direction at the same rate. Okay? So let's take into account this idea that K, this equilibrium constant, is equal to the products divided by the reactants. Well, what that tells me is K is equal to the concentration of B at equilibrium times the concentration of C, those are my products, at equilibrium, divided by the concentration of A squared. Why does A get the squared? Well, because of my stoichiometry in the balanced equation. Okay, so now that I have my K expression, this is my equilibrium expression. I can actually plug in concentrations at equilibrium, and I wrote those in for us, but it's whatever the concentration is when the graph is leveled off. So B is 0.32 molar, C is 0.12 molar, divided by A, which is 0.15 molar squared. When I plug all of this in my calculator, I get K equals 1.7. Okay, so that is my equilibrium expression and my equilibrium value when I plug in. And see, in this case, K is bigger than 1, which means our products are favored at equilibrium. Does the graph support that? Well, look at when the graph levels off. Do we have more products than reactants? Well, B and C are the products. Look at B is at a higher concentration, C is lower, but overall, we obviously have more products than A, the reactant, at equilibrium. So I agree that the products are favored. So what does K mean, right? Why are we solving for this K value? Well, if K is greater than 1, it means at equilibrium, there are more products than reactants. So what we say is that the reaction is favored to the right. So that forward reaction is favored. If K is less than 1 at equilibrium, there are more reactants than products, which means we say the reaction is favored to the left. Let's look back. So again, we'll use this. K bigger than 1 means our products are favored. K less than 1 means our reactants are favored at equilibrium. All right, here's another graph, and I want you to write the balanced chemical equation, write the K expression, solve for K, and then tell me what K means. Are products favored or are reactants favored? So I'm going to first see. All right, so I'm going to first see where my graph levels off. And let's say that that's right about 800 seconds. I think maybe it's a little before, but close enough. And I'm going to highlight my equilibrium section, right? That's where the graphs are flat. That means the concentrations aren't really changing much. The forward rate and the reverse rate are equal. And then I did a little work for us ahead of time. So here's what I did. I looked at the change in A. So A started at a concentration of 0.8 molar and it ended at 0.2. So that means the change was 0.6 molar. I did the same for C. C is being produced. It started at 0 and it ended at 0.3. So the change for C was 0.3 molar. This helps me write my balanced chemical equation because I can see that A is changing twice as fast, right? 0.6 is double 0.3. So I'm going to get 2A making C. I know A is a reactant because it's being used up. C is a product because it's being made. And I know there's a 2 in front of A because it changed double the amount that C changed. All right, so now we can write our equilibrium expression. So there's my balanced equation. The K expression is equal to products, which is my C, concentration of C, divided by my reactants, which is A squared. Okay, we can also solve for K. K equals, and at equilibrium, the concentration of C is at 0.3 molar, and the concentration of A is 0.2 molar, and that guy is squared. This means that K equals 7.5. Notice K does not have any units, right? Because as we square things, it could, each expression is a little different, basically. The convention is to not put units on big K, which is a nice difference from our last unit. So we solve for K. What does K mean? Well, I noticed that K is bigger than 1, which means the products are favored at equilibrium. Let's check back at the graph. Is that what it looks like? Is at the equilibrium, the highlighted, is the product C at a higher concentration than A? Yes, it is. So that supports our answer. For this problem, I just want you to look at the graph and predict if K is bigger than 1 or less than 1. So we can put our equilibrium line, maybe like right in here somewhere. We get leveled out. So I'm looking, A is being used up, so it's a reactant. B and C are products because they're forming. So looking at this graph, at equilibrium, who do we have more of? Well, we have more of B and C. Okay, remember, K is equal to the concentration of the products divided by the concentration of the reactants. So if it looks like we have a bigger concentration of products, right, this guy is bigger, that means products are favored at equilibrium, which means K is bigger than 1. In order for the K to be bigger than 1, the products have to be a larger number, which they are. All right, so let's talk a little bit more about the equilibrium constant. That's big K. You might also see KEQ. EQ is for equilibrium, or KC, and KC stands for concentration. Later this unit, just a heads up, we'll also see KP, and P stands for partial pressures. Same exact thing, except instead of plugging in concentrations, we'll plug in pressures. But all of these things are going to mean the same thing for us, these big Ks, so don't be thrown off if I ask for KEQ or KC. I'm just asking for K. So we have our balanced equation. The big letters are representing the chemicals involved in the reaction, and the little letters are representing the stoichiometry, the balanced equation. So our equilibrium constant, Kc, is equal to the products raised to the power of the stoichiometry divided by the reactants raised to the power of their stoichiometry. And these square brackets are important because they're telling me that we're measuring the concentration at equilibrium, right? Molarity or mole divided by liter. So make sure you put each species in square brackets. All right, so try to write the equilibrium expression for this guy, pause the video, and then on the next slide you can check your answer. Hopefully this is what you got. Remember, Kc is equal, or K is equal to the products. So concentration of NO squared because of that 2 divided by the reactants. So the concentration of N2 times the concentration of O2. Those are just raised to the power of 1. You don't need to write that, but no exponent because they are in the balanced equation. The stoichiometry is 1 to 1. All right, hopefully you're getting this. Pause the video and try this one. All right, hopefully you paused the video and tried, and now you're kind of looking at your computer screen or your cell phone confused because I told you that the equilibrium is products divided by the reactants, and there's one product, this guy, and one reactant, this guy, missing. That's interesting. The reason that they are missing is because we don't put solids, no sneaky solids, in the equilibrium expression. As you see, this guy is a solid, this guy is a solid. Sneaky solids are not allowed. They do not impact the equilibrium position, so they don't go in the equilibrium expression. For those of you who are why kids, like why don't we put solids? The reason solids don't go in the expression is because when you use up a solid, so let's say we're starting with this nickel oxide and some of it gets used up. What's happening when we use up a solid is that we are changing the number of particles, right? We're reducing the number of particles and we're reducing the volume, the size of it. So if I'm lowering the number of particles and I'm lowering the size, we're not actually changing concentration, right? If I lower the top of the equation and the bottom, concentration is still going to stay the same. Or you could think about it as density. The density of this does not change when I make it smaller, when I cut the piece out. So the using up of a solid does not impact the equilibrium position, so K is not impacted. All right, no more tricks. Try this one. Make sure we fully get it. Pause the video. Write your K expression, your equilibrium expression. All right, I lied. One more trick. This guy, we have our products on this side here. But notice, water, H2O, is not written in the equilibrium expression. We included both reactants, the aqueous and the gas, but we did not include water. Let's see why. So we know now that no sneaky solids are allowed, but the same rule applies for, I call them sly liquids. No liquids allowed in the equilibrium expression. The reasons for you why kids that we leave out liquids is because if we take out, let's use water as our example, if we add or take out water with this reaction happening in aqueous solution, it does not really change the concentration of the water, right? That's not impacted because there's tons of water everywhere. So removing or adding a liquid is not impacting the concentration at all. It doesn't change it. So here's kind of the big takeaways. The equilibrium expression is K equals the concentration of the products at equilibrium divided by the concentration of the reactants at equilibrium. When we write these K expressions, we include gases and aqueous species, but we do not include sly liquids or sneaky solids.